Hello everyone. I hope you all are well and making progress in life. Here is Priyanshu and welcome to the Infinity Mind. So today I will be solving the problem inversion count. So the problem statement says that for a given array of size n containing all distinct values, find the total number of inversions that may exist. The An inversion is defined for a pair of integers in the array when the following two conditions are met. Array of I is greater than array of j and I is less than j. It means that we have given an array and we have to count the pairs such that left element is greater than the right element. Alright, so we can see here in the sample input 1 we are given 3 to 1 and we have a total of 3 pairs which satisfy the condition left element is greater than the right element. That's why I is less than j and ARR of I is greater than ARR of j conditions are given. So here the pairs are 3 comma 2, 2 comma 1 and 3 comma 1. In the sample input 2 we can see there are total 4 pairs 2 comma 1, 5 comma 1, 5 comma 3 and 5 comma 4. Alright, so we have to find this. So what can be the most brute force approach? The most brute force approach can be checking all the pairs. Yes, we can check all the pairs. So suppose we are given the array 2, 5, 1, 3 and 4. We can stand here and check for all the elements. I mean we can check for all the pairs, like if I is here, when we then we can go then we can take j from the next element, that is j is equals to I plus 1 to the end, and we can check which pair satisfies the condition, that which pair says that I is array of I is greater than array of j. All right, and similarly we will keep iterating I up to the end and we will check the condition, but this will take big O of n square time complexity, and in our constraint it is given that n is from 1 to 10 to the power 5, and we know that this will not be running in big O of n square, so we need to optimize it. So we need to optimize in either big O of n log n or less than this. So let's try to optimize this. So what we can think of it? So we are just given an array. Let me take the example, the second example, 2, 5, 1, 3, 4 here in the whiteboard. So here we have 2, 5, 1, 3 and 4, and we have to count the pairs where left element is greater than the right element. So we all must be thinking that how is it possible without checking all the pairs, because these are not, the array is not sorted, and if we sort it we cannot do it because the element's position will be disturbed. So by this using this array only we have to count the number of such pairs. So without big of n square time complexity, without using pairs, without checking all the pairs, how can we say that how can we calculate the number of inversion counts? So it means we have to check all the pairs. So how can we check optimally? So can we say, let's say if I'm standing here, if I'm standing here at 3, I need to check all the elements before 3 that are greater than 3. So we can say yes, 5 is greater than 3, and all the elements, let's say we have to start now. Wait, I'm explaining. We have to check all the elements starting at a current element, we have to check all the elements which are greater than the current element before the current element. So if we are standing here at 2, we need to check all the elements before 2 that are greater than 2, that is 0. Let's take a count variable, this is 0. And now we are here, all the elements greater than 5 before 5, 0. Here all the elements greater than 1 before 1, yes, 2 and 5, so count is increased by 2. All the elements greater than 3 before 3, yes, only 1, that is 5, so count is increased by 1. All the elements greater than 4 before 4, yes, 5, so here count, here it is became 4, so count is 4. So our answer was also 4. But for checking all the elements before any element, all the elements greater than the current element before this element, we have to check all the elements. Alright, so this will take big of n square. But how can we optimize this? The constraint was 10 to the power 5, and in 1 second we are allowed only 10 to the power 7 operations. So we have to do this in O of n log n time complexity. So how can we think of it? We need to anyhow optimally check for this. So this is a classic question. We can do this through merge sort. Let me tell you how. If we all know what's a merge sort and we all know how does this works, so we have the same 2 5 1 3 4. What does merge sort do? We just, in the merge sort, it divides the array in two parts. This is a divide and conquer algorithm, so we divide the array in two parts. Again 2 5 will be divided in two parts, 2 5 and 1, and this will be divided in 3 and 4. Alright, these are all. Let me draw this also, and we keep it divided until we find only one element. Alright, so let me fully divide it, 2 and 5. Now what we do in merge sort, we divide it, and now when we reach the base case, we start merging. Now we merge it, so this 2 and 5 becomes, after sorting, this becomes, it starts merging, and merging, not normal merging, it merges such a way that it becomes sorted. And similarly this now 2 and 5 will merge to 1. Let me write above directly only. I should not write here. I should merge then above only. So 2 and 5 will be merged as in ascending order. Now 1 will also be merged, so this will be now sorted. We all know the merge sort algorithm. If we don't know, we can check on YouTube or check on my channel, merge sort algorithm. Or alright, so we all know already what's a merge sort, just dividing and dividing and dividing and just again merging. So now here also 3 and 4 will be merged, and now at the end we will get here, let me erase this, the sorted array 1 2 3 4 5. So what's the logic here? What we can do while merging, what we can do, we can check, let me do separately what I'm trying to say. Suppose we have two arrays, two separate arrays, 1 2 and 5. We will do this during merging, and this is a separate array 3 and 4. Alright, now if we keep I pointer here and j pointer here, and if we check if what does during merging it says, it merges. We use a temporary array for merging. So while merging, we push the smaller element into the array. All right, suppose we the two separate arrays are these, and while merging them, we use two pointers left and right. So I've used here I and j. What we do, we just use a temporary array, and we just push back the smaller element in the array I among I and j, and we keep moving I and j accordingly. So here 1 and 3, I the element which is smaller, we push back into temporary array. So 1 will be 1 is less than 3, so we will push back 1. All right, and now I will be moved here, and now 2 and 3, 2 will be pushed and I will be moved here. Now 5 and 3, in this case we have we have seen that this I is greater than this j. So if we have to count if we have to maintain the count, let's say count is 0 now, the number of inversion counts, that the condition you all know what is an inversion count. So can we say that this array of left has become greater than array of j? What I told in the starting, that we want the element greater than this right side element. We want the left element greater than the right element. So if we found any left element greater than the right element from these two separate arrays, using these two separate arrays, we can say that 5 is greater than 3. So can we say that we have found a count 5 is greater than 3? We say that we have found a pair 5 and 3. So yes, we can increase the count by 1, but not by 1. We should what if the array was more? What if array was larger? So this, we all know, this was till mid. The first array was from starting to the mid, and this second array was mid plus 1 to the ending. So can we say that all the elements from this was sorted array? So can we say that all the elements here will be greater than this 3? So can we say, instead of increasing count by just 1, we can directly increase the count by mid minus I plus 1, because all the elements between mid and I will be mid minus I plus 1, total number of elements. So can we increase our we should increase our count with this. All right, now again if we move j here, so yes, 5 is greater than 4. Now also we will increase our count by mid minus I plus 1. Now this j will be exhausted and we will end, and at merge while doing merging, we will just also handle the case where one array exhausted and we should fill the other array also. So if I tell you the main logic, this was just we just have to do one single change, not a single change, I would say. We have to just add a single line of counting the inversion. We have to just add this we just have to add the single line, the single line of code this of this inversion count when we find any element in the first array greater than the element in the second array. So we will just say we have found a pair, and we will just increase our inversion count. All right, so this inversion count will be increased with mid minus I plus 1. So the intuition was this only, that where we are standing, we just have to find number of elements greater than, suppose we are standing at 3 so we have to find the number of elements which are greater than 3 and before 3. So here it is only 5. So that was taking big of n square time complexity for finding pairs. But while doing merge sort, we can see like from starting from the below to 2 and 5, they are in correct order. So before merging we can check. All right, so from starting before merging I said, so 2 and 5 we can check here also. 2 is not greater than 5, we will not increase our count. But after merging here we have got the new case 2, 5 and 1. Now we just need to check the elements here. We need to check elements greater than 1 before the 1, and before the 1 we have got the elements that are already sorted. So this can be, this operation which I am telling you, this can be done in the size of this smaller array is n1, and this the if the size of this first array is n1 and second is n2, we can do this in big O of n1 plus n2. Alright, so this merge sort, while writing the merge function of the merge sort, this inversion count becomes easy than our previous big O of n square. Here we adding just single n of code, we can do this in big O of n log n. So that's was this was the whole dry run. Yes, if yes, I I think I have done the dry run also here. This 1 to 5, where here we have got 5, so this was greater than 3, so we add in count mode minus I plus 1, that is 1. And now again here also we will add, we have found 5 greater than 4, we will again add 1. Similarly, if I show you the whole dry run, starting from here, our count was 0. All right, so 2 is not greater than 5, I will be here and j will be here. So 2 is smaller than 5, no, nothing, and this will exhaust and count will be 0. Now from here I will be here and j will be here. 2 is greater than 1, yes, we have found an element and this was mid, so count will be increased with, if 2 is greater than 1, 5 is also greater than 1, so count will be increased with 2 because we have found 2 elements. Now j is here, so in this case in the merge function j will be pushed, and so j will be increased, so it will be exhausted now. So in if we see here also 3 is less than 4, nothing will happen, count will remain the same. But in this case I will be here, j will be here. I have done this dry run here only, in the below I have done the dry run, so here we have got count 2 elements were there. Let's do here also, no problem. J was here, so 1 is less than 3, so 1 will be pushed back into the temporary array, so I will be increased. Now 2 is less than 3, again I will be increased. 5 is greater than 3, so count will be increased by 1, all the elements including 5 and after 5, so count will be increased by 1, this will be 3. Now again j will increase, so 5 is greater than 4, again this will be increased by 1, this will be 4. So we can see the count is now 4, and we have got our answer also. So this was the whole dry run. You can do dry run on your own also. So let's go to the implementation part now. So what I said, we just have to use the merge sort function. So let me call the merge sort function, and there we pass array, the starting and the ending. All right, so we have to return answer also in long form, so long, let the answer is count, and we are passing long indexes, so I should write here 0 ll, no problem, and we can return the answer. Now if I write the merge sort function, this will return long and merge sort. Here I am passing arr and start and ending. All right, now here I declare the count. Let's say it's 0, and if this is just the merge sort function, not nothing else. Now if start is less than end, we first we have to find mid. All right, we are dividing here, so mid will be nothing but start plus and minus start divided by 2, and we have to just call the merge sort function again for the first half of the array. So the first half of the array will pass as first of all array, then first half of the array will be from 0 to mid, and merge sort the second half of the array will be from mid plus 1 to the end, and then we will merge them. So merging them, we will pass the starting is not 0, starting is start, and this will be start, this will be mid, and we will pass end. And yes, we have to increase our count also if we find any, because it's a recursive function, so many merge sort will call, and they will return long. So now at the end we will just return count, and now similarly we will write merge function also. This is just merge function, nothing else. This is just merge sort function overall. So here we will pass array and start, mid, end. If I'm missing anything, no. Now we have to take 2 pointers. I will take everything long because I don't want to take risk. I take everything as long. Now left will be our starting, and right pointer will be our ending. No, left the starting index of the first array is a start, and the starting index of the right array will be mid plus 1. And let's count also what I said. While yes, we are just adding the normal merge sort function. Left is less than equal to mid, and right is less than equal to end. If we see any element left is less than equal to any element right, yes, we have to also use a temporary array also. We you can remember the merge sort function, we use temporary array also. So this temporary array will use, so this will push back the array of left, the smaller element, and we will not forget to increase our pointer. Now similarly in the else case, now this is the case where we will find array of j is greater than array of I is greater than array of j. This is the case where left element will be greater than the right element. So in this case we will push back also the smaller element, and we will move our pointer also. But what I said, we have to increase our inversion count. So what was our inversion count? Our inversion count was mid minus I plus 1. Mid minus I plus 1. What was I? I was left pointer, so this was left. Alright, so now handling the edge cases when one array get exhausted. Suppose left array is left, I mean right array was exhausted, so we have to take care of left array also. So this will just, this is just merged sort function. We can just copy and paste also, but right now I'm practicing, that's why I'm writing the whole code. Right is less than, and so I will copy this. You can have a dry run on your own also, and at last we are salting, so that's why I'm using everything as long. That's why we have to we have to update our original array. The temp array contains the salted one, but we have to update our original array. So array of I plus starting will be temp of I. Now we'll just simply return count, and here also we will simply return count, and here we are returning it. So let's run and see whether we are able to pass the sample test cases. Alright, so the problem was I was declaring the array incorrectly. I just declared the array pointer incorrectly, so I am now correcting it. Just shift of pointers, a silly mistake. Now let's run this and let's check if we are able to pass the sample test cases, and yes, now let's submit it, and yes, we are able to pass this pass the sample test, the pass. Now yes, we are able to pass all the test cases, and yes, this problem is solved, and yes, this problem was some, it was just an easy problem for big of n square time complexity, but this problem was typical and some logical problem. This was a classic, I would say this was a standard classic problem for inversion counts. Alright, so this was all about this problem, and time and space complexity we all know that this here we are just using merge sort function, and merge sort function is just has time complexity of big of n log n, and space complexity of that temporary array we use in merge sort, so that's big of n space complexity. So we can see how we just uh, coded just the merge sort function, and just make a one small change here only, where we just have to count the number of pairs. So just one small line of code we had added in this inversion count, and our problem is solved. So this was all about this problem. Thanks for watching. Till then, keep learning and keep upgrading yourself. See you in the next video.